Hello. For this video, we're going to be looking at forces for the incline plane, which is a common problem in introductory physics for forces, and it can be very tricky because you have to involve some trigonometry. But here are the general steps for this problem. As with any kind of force problem, you want to draw a picture or a force diagram. And in that picture, you're going to draw several things. First, you want to identify the direction of motion because that's going to influence what friction is doing. And then you want to identify all the forces present and their respective directions. So, for example, gravity is always acting downward, friction's always opposing the direction of motion, the normal force is perpendicular to any surface of contact, that sort of thing. And the next one is very important for this inclined plane problem, which is choosing a coordinate system. Because when forces are all horizontal and vertical, you can get away with just using the standard horizontal as x, vertical as y. But when you're dealing with the inclined plane, you're going to have to rotate your coordinate system for a couple reasons. It will limit the directions of motion and force to a single direction, and thus causing the net force in another direction to equal zero. If you didn't rotate the coordinate system, you would have to add constraints where you're linking the x and y accelerations, and it would just be a big mess at the end. Once you've drawn those forces and the coordinate system, then you'll get into the actual physics where you put those forces into F equals ma equations for each direction. Before we get into the actual inclined plane, let's look at what happens when we examine forces just across a flat surface and see what gets adjusted as soon as we put that on an incline. So here we are, we're going to push this box to the right. So I say, okay, our direction of motion is going to be to the right in the direction of our push. Well, if we're pushing one way and we're moving, well, more importantly, if we're moving to the right, that means friction's going to the left. You could have a case where you're pushing one direction with the friction. So let's say you're at the bottom end of a block that's sliding down, you want to push that up. But friction's always going to oppose the direction of motion no matter what. Then we have gravity going down because we're on Earth, and the normal force is always acting perpendicular to the surface. And so since our surface is perfectly horizontal, the normal force is perfectly vertical. And because all our forces are horizontal and vertical, we can get by with just doing the horizontal and vertical coordinate system where I say, okay, plus x, that'll be the direction of motion and the push, minus x would be friction, normal force is plus y, and gravity is in the minus y direction. So we've identified direction of motion, our forces, and our coordinate system. Next thing we need to do is insert that into F equals ma equations. And to help with that, I'm going to remove all the extraneous stuff, all the white things that are the picture, and we're just going to be left with our coordinate system and forces. And when we do that, we have that picture on the left just has a coordinate system and our forces. And we'll put those forces into F equals ma equations. If we look at the x direction, sum of the forces in x is equal to mass times acceleration in the x direction. We don't have a way of knowing whether or not this is 0 or some value, so we'll leave it as an unknown. And we're pushing one way and friction's going the other way. And in introductory physics, we'll say that the force of friction between solid objects is a coefficient of friction times the normal force. Then when we look at the y direction, as long as this box is staying on the surface, the forces in the y direction have to cancel each other. Otherwise, it would be floating away or crashing through the earth. So sum of the forces is in the y direction is equal to 0. We have normal force going up and gravity going down. They cancel each other, and a lot of times normal force is just labeled with N. Force of gravity is mass times the gravitational acceleration. So you can rearrange this to solve for the normal force and then put that normal force into the x direction equation to eventually solve for the acceleration in the x direction. So that's what's going on when you have an object on the flat level surface. Now let's look at what goes on when we decide to push this up an incline. So what will happen is gravity is always going to act downwards no matter what. But now, since the object is on an incline, the direction of our push, the direction of friction, and the normal force are going to be different. So let's look at that. So let's say we're pushing this box up an incline. So we'll have the direction of motion going up. In this case, we're pushing it up the incline. Friction is pushing it down the incline. Gravity is always acting vertically downwards. And because our block is now at an angle, the normal force is also going to be at an angle because the normal force is always perpendicular to the surface of contact. So we've identified the forces, now let's draw a coordinate system. And so for the incline problem, we're going to have the x direction be along the incline and the y direction being perpendicular to the incline. The reason for that is because the forces perpendicular to the incline have to cancel out as long as this block is staying on it. So let's draw those axes. We have the y-axis, again, going perpendicular to the incline along the normal force, and the x direction is going along the direction of motion. It's the same direction as the push and friction. However, gravity is always acting vertically downwards, and so in this scenario, gravity is going to be acting in both the x and y directions in this coordinate system. So then that begs the question, okay, well, how do you get those x and y components of gravity in this new coordinate system? What you can do is just superimpose dotted lines that would be the horizontal and vertical. And what you end up finding is this angle of inclination down here, you can transpose the angle, and it's this same angle up here that the horizontal makes with the push, because the push is going straight up the incline at that angle. And you can apply a little bit of trigonometry and say if this angle is theta and you have a right angle here, this angle is also theta that gravity makes with the y direction. So this angle of inclination is the same angle that the push makes with respect to the horizontal, and just transposing that angle, it's the same angle that gravity makes with this rotated coordinate system. So let's strip away some of the illustrations and just leave ourselves with the forces, the coordinate system, and the horizontal and vertical. So this is what it looks like when we do so. Again, the angle of inclination for the incline is the same angle that the push makes with the horizontal, and hopefully you can see it a little bit better. It's the same angle that gravity makes with this rotated y coordinate. And if you want the y component of gravity in this coordinate system, the y component of gravity is the adjacent side of this angle. So the y component of gravity is you're going to use the cosine, and the x component of gravity in this coordinate system is the opposite side of the angle. And so for the x component of gravity in this coordinate system, you're going to use the sine because it's the opposite side. You can always fall back to the base definitions of your trig identities here, where sine always means opposite over hypotenuse and cosine always means adjacent over hypotenuse. So let's shrink this and then put our forces into F equals ma equations. So let's start with the x direction. So our x direction is plus x is going up the incline, minus x going down the incline. And we don't know what the acceleration is along the incline, so we'll leave that as an unknown. we're pushing up the incline, and the direction of motion is up, so friction is going to go down. And gravity, even though it's acting vertically downwards, there's a x component to it in this rotated coordinate system. And because the x part of gravity in this rotated coordinate system is the opposite side of the angle, we're going to use a sign to get that. So our x component of gravity in this coordinate system is mg sine theta. Friction is still coefficient of friction times the normal force, although our normal force is going to be different in this case. When we look at the y direction, again, as long as this block stays on the incline, the forces in the y direction have to cancel each other. So the net force in the y is 0. We have normal force going perpendicular to the incline, it's always perpendicular to the surface of contact. And gravity is acting vertically downwards and partially in this rotated y coordinate. And to get the y component of gravity in this coordinate system, it's the adjacent side of this angle, so we're going to use a cosine. So our normal force is n. We want the y component of gravity in this coordinate system, which is the adjacent side of this angle. That'll give us a cosine theta. So now our normal force in this inclined plane is a little different. It's equal to mg cosine theta, and then you can insert this normal force up here in the x direction equation to get the acceleration of the object. But again, the key thing here is we rotate this coordinate system. This limits our motion to only one coordinate direction, so we only have acceleration in x, no net force in y, and the push is only in x, the friction's only in x, the normal force is only in y, but gravity acting vertically downward is going to be partially in x and partially in y in this rotated coordinate system. And to get the x part of gravity, we use the sign because it's the opposite side of the angle. And to get the y component of gravity, we use the cosine because it's the adjacent side of the angle. So to recap, our general steps for approaching forces on the inclined plane as well as any kind of force problem. First, you want to draw a picture, and in that picture you want to identify the direction of motion, all the forces and their directions. Friction's always opposing the direction of motion, gravity's always acting vertically downward, and the normal force is always perpendicular to the surface of contact. Once you've drawn those forces, then you want to draw and choose a coordinate system. And for this inclined plane, you want to rotate the coordinate system so the x is only along the incline and the y is perpendicular to the incline. This limits motion to only one coordinate direction, and you can say the net force in the y direction is 0. Consequently, you have to split gravity into x and y components for this coordinate system. And once you do that, you can insert your forces into F equals ma equations for each direction and solve the problem. Again, this will take some practice doing. You can always rely on the base definitions of your trig identities when trying to figure out how to separate gravity as well as any other force that's at an angle.